Section number 1 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Marie Nielsen, Vancouver, BC. Light Science for Leisure Hours by Richard A. Proctor. Prefaces. Preface to the 5th edition. In preparing this edition, only those passages which have been shown by recent researches to be erroneous have been removed. It has not been thought necessary, or even desirable, to modify the wording of essays, by changes of tense or otherwise, in such a way that, as thus modified, the essays might have appeared in 1884. In many cases this would have been altogether misleading, whereas, with the dates prefixed to the several essays, no misconceptions can arise. Preface to 2nd edition. This edition has been carefully revised, and, in parts, considerably modified. Thus the essays on Britain's coal cellars has been added, and 2 essays on government aid to science have been removed. I may mention that my views on the subject of the last named essays have changed altogether since those essays were written. Certain circumstances which have come under my observation have convinced me that more mischief than advantage would result from any wide scheme for securing government aid for scientific researches. London, January 1873. Preface to the 1st edition. In preparing these essays, my chief object has been to present scientific truths in a light and readable form, clearly and simply, but with an exact adherence to the facts as I see them. I have followed, here and always, the rule of trying to explain my meaning precisely as I should wish others to explain to myself matters with which I was unfamiliar. Hence I have avoided that excessive simplicity which some seem to consider absolutely essential in scientific essays intended for general perusal, but which is often even more perplexing than a too technical style. The chief rule I have followed, in order to make my descriptions clear, has been to endeavour to make each sentence bear one meaning, and one only. Speaking as a reader, and especially as a reader of scientific books, I venture to express an earnest wish that this simple rule were never infringed, even to meet the requirements of style. It will hardly be necessary to mention that several of the shorter essays are rather intended to amuse than to instruct. The essay on the influence which marriage has been supposed to exert on the death rate is the one referred to by Mr. Darwin at page 176, volume 1 of his Descent of Man. London, May 1871. End of section 1. Recording by Linda Marie Nielsen, Vancouver, BC.
Section 2 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Tyler Farmer. Light Science for Leisure Hours by Richard A. Proctor. Strange Discoveries Respecting the Aurora. The brilliant streamers of colored light which wave at certain seasons over the heavens have long since been recognized as among the most singular and impressive of all the phenomena which the skies present to our view. There is something surpassingly beautiful in the appearance of the true auroral curtain. Fringed with colored streamers, it waves to and fro as though shaken by some unseen hand. Then from end to end there pass a succession of undulations, the folds of the curtain interwrapping and forming a series of graceful curves. Suddenly, and as by magic, there succeeds a perfect stillness, as though the unseen power which had been displaying the varied beauties of the auroral curtain were resting for a moment. But even while the motion of the curtain is stilled, we see its light mysteriously waxing and waning. Then, as we gaze, fresh waves of disturbance traverse the magic canopy. Startling coruscations add splendor to the scene, while the noble span of the auroral arch, from which the waving curtain seems to depend, gives a grandeur to the spectacle which no words can adequately describe. Gradually, however, the celestial fires which have illuminated the gorgeous arch seem to die out. The luminous zone breaks up. The scene of the display becomes covered with scattered streaks and patches of ashen gray light, which hang like clouds over the northern heavens. Then these in turn disappear, and nothing remains of the brilliant spectacle but a dark, smoke-like segment on the horizon. Such is the aurora, as seen in Arctic or Antarctic regions, where the phenomenon appears in its fullest beauty. Even in our own latitudes, however, strikingly beautiful auroral displays may sometimes be witnessed. Yet those who have seen the spectacle presented near the true home of the aurora recognize in other auroras a want of the fullness and splendor of color which form the most striking features of the Arctic and Antarctic auroral curtains. Physicists long since recognized in the aurora a phenomenon of more than local, of more even than terrestrial, significance. They learned to associate it with relations which affect the whole planetary scheme. Let us inquire how this had come about. So long as men merely studied the appearances presented by the aurora, so long, in fact, as they merely regarded the phenomenon as a local display, they could form no adequate conception of its importance. The circumstance which first revealed something of the true character of the aurora was one which seemed to promise little. Arago was engaged in watching from day to day, and from year to year, the vibrations of the magnetic needle in the Paris observatory. He traced the slow progress of the needle to its extreme westerly variation, and watched its course as it began to retrace its way towards the true north. He discovered the minute vibration which the needle makes each day across its mean position. He noticed that this vibration is variable in extent, and so he was led to watch it more closely. Thus he had occasion to observe more attentively than had yet been done the sudden irregularities which occasionally characterize the daily movements of the needle. All this seems to have nothing to do with the auroral streamers, but we now reach the important discovery which rewarded Arago's patient watchfulness. In January 1819, he published a statement to the effect that the sudden changes of the magnetic needle are often associated with the occurrence of an aurora. I give the statement in his own words, as translated by General Sabine. Auroras ought to be placed in the first rank among the causes which sometimes disturb the regular march of the diurnal changes of the magnetic needle. These do not, even in summer, exceed 1/4 of a degree, but when an aurora appears, the magnetic needle is often seen to move in a few instants over several degrees. During an aurora, he adds, one often sees in the northern region of the heavens luminous streamers of different colors shoot from all points on the horizon. The point in the sky to which these streamers converge is precisely the point to which a magnetized needle suspended by its center of gravity directs itself. It has, moreover, been shown that the concentric circular segments, almost similar in form to the rainbow, which are usually seen previous to the appearance of the luminous streamers, have their two extremities resting on two parts of the horizon which are equally distant from the direction towards which this needle turns, and the summit of each arc lies exactly in that direction. From all this, it appears, incontestably, that there is an intimate connection between the causes of auroras and those of terrestrial magnetism. This strange hypothesis was, at first, much opposed by scientific men. Amongst others, the late Sir David Brewster pointed out a variety of objections, some of which appeared at first sight of great force. Thus, he remarked that magnetic disturbances of the most remarkable character have often been observed when no aurora has been visible, and he noticed certain peculiarities in the auroras observed near the polar regions, which did not seem to accord with Arago's view. But gradually it was found that physicists had mistaken the character of the auroral display. It appeared that the magnetic needle not only swayed responsively to auroras observable in the immediate neighborhood, but to auroras in progress hundreds or even thousands of miles away. Nay, as inquiry progressed, it was discovered that the needles in our northern observatories are swayed by influences associated even with the occurrence of auroras around the southern polar regions. In fact, not only have the difficulties pointed out very properly, it need hardly be remarked, by Sir David Brewster been wholly removed, but it has been found that a much closer bond of sympathy exists between the magnetized needle and the auroral streamers than even Aracle had supposed. It is not merely the case that while an auroral display is in progress, the needle is subject to unusual disturbance, but the movements of the needle are actually synchronous with the waving movements of the mysterious streamers. An aurora may be in progress in the north of Europe, or even in Asia or America, and as the colored banners wave to and fro, the tiny needle, watched by patient observers at Greenwich or Paris, will respond to every phase of the display. And I may notice in passing that two very interesting conclusions follow from this peculiarity. First, every magnetic needle over the whole earth must be simultaneously disturbed, and secondly, the auroral streamers which wave across the skies of one country must move synchronously with those which are visible in the skies of another country, even though thousands of miles may separate the two regions. But I must pass on to consider further the circumstances which give interest and significance to the strange discovery which is the subject of this paper. Could we only associate auroras with terrestrial magnetism, we should still have done much to enhance the interest which the beautiful phenomenon is calculated to excite. But when once this association has been established, others of even greater interest are brought into recognition. For terrestrial magnetism has been clearly shown to be influenced directly by the action of the sun. The needle in its daily vibration follows the sun, not indeed through a complete revolution, but as far as the influence of other forces will permit. This has been abundantly confirmed and is a fact of extreme importance in the theory of terrestrial magnetism. Wherever the sun may be, either on the visible heavens or on that half of the celestial sphere which is at the moment beneath the horizon, the end of the needle nearest to the sun makes an effort, so to speak, to point more directly towards the great ruling center of the planetary scheme. Seeing, then, that the daily vibration of the needle is thus caused, we recognize the fact that the disturbances of the daily vibration may be referred to some peculiarity of the solar action. It was not, therefore, so surprising, as many have supposed, that the increase and diminution of these disturbances, in a period of about 11 years, should be found to correspond with the increase and diminution of the number of solar spots in a period of equal length. We already begin to see, then, that auroras are associated in some mysterious way with the action of the solar rays. The phenomenon which had been looked on for so many ages as a mere spectacle, caused perhaps by some process in the upper regions of the air of a simply local character, has been brought into the range of planetary phenomena. As surely as the brilliant planets which deck the nocturnal skies are illuminated by the same orb which gives us our days and seasons, so they are subject to the same mysterious influence which causes the northern banners to wave resplendently over the starlit depth of heaven. Nay, it is even probable that every flicker and coruscation of our auroral displays corresponds with similar manifestations upon every planet which travels around the sun. It becomes, then, a question of exceeding interest to inquire what is the nature of the mysterious apparition which, from time to time, illuminates our skies. We have learnt something of the laws according to which the aurora appears, but what is its true nature? What sort of light is that which illuminates the heavens? Is there some process of combustion going on in the upper regions of our atmosphere? Or are the auroral streamers electric or phosphorescent? Or lastly, is the light simply solar light reflected from some substance which exists at enormous elevation above the earth? All these views have, from time to time, found supporters among scientific men. It need hardly be said that what we know now of the association between auroral action and some form of solar disturbance would at once enable us to reject some of these hypotheses. But we need not discuss the subject from this point of view, because a mode of research has recently been rendered available, which at once answers our inquiries as to the general character of any kind of light. I proceed to consider the application of this method to the light from the auroral streamers. The spectroscope, or, as we may term the instrument, the light sifter, tells us of what nature an object which is a source of light may be. If the object is a luminous solid or liquid, the instrument converts its light into a rainbow-colored streak. If the object is a luminous vapor, its light is converted into a few bright lines. And lastly, if the object is a luminous solid or liquid shining through any vapors, the rainbow-colored streak again makes its appearance, but it is now crossed by dark lines, corresponding to the vapors which surround the object and absorb a portion of its light. But I must not omit to notice two circumstances which render the interpretation of a spectrum somewhat less simple than it would otherwise be. In the first place, if an object is shining by reflected light, its spectrum is precisely similar to that of the object whose light illuminates it. Thus, we cannot pronounce positively as to the nature of an object merely from the appearance of its spectrum, unless we are quite certain that the object is self-luminous. For example, we observe the solar spectrum to be a rainbow-colored streak crossed by a multitude of dark lines, and we conclude accordingly that the sun is an incandescent globe shining through a complex vaporous atmosphere. We feel no doubt on this point, because we are absolutely certain that the sun is self-luminous. Again, we observe the spectrum of the moon to be exactly similar to the solar spectrum, only, of course, much less brilliant. And here also we feel no doubt in interpreting the results. We know, certainly, that the moon is not self-luminous, and therefore we conclude with the utmost certainty that the light we receive from her is simply reflected solar light. So far, all is clear. But now take the case of an object like a comet, which may or may not be self-luminous. If we find that a comet's spectrum resembles the sun's, and this is not altogether a hypothetical case, for a portion of the light of every comet yet examined does in reality give a rainbow-colored streak resembling the solar spectrum, we cannot form, in that case, any such positive conclusion. The comet may be a self-luminous body, but on the other hand, its light may be merely due to the reflection of the solar beams. Accordingly, the spectroscopist always accompanies the record of such an observation with an expression of doubt as to the real nature of the object which is the source of the light. Secondly, when an electric spark flashes through any vapor, its light gives a spectrum which indicates the nature, not only of the vapor through which the spark has passed, but of the substances between which the spark has traveled. Thus, if we cause an electric flash to pass between iron points through common air, we see in the spectrum the numerous bright lines which form the spectrum of iron, and in addition, we see the bright lines belonging to the gases which form our atmosphere. Both the considerations above discussed are of the utmost importance in studying the subject of the auroral light as analyzed by a spectroscope, because there are many difficulties in forming a general opinion as to the nature of the auroral light, while there are circumstances which would lead us to anticipate that the light is electric. I notice also in passing that we owe to the Swedish physicist Ångström a large share of the researches on which the above results respecting the spectrum of the electric spark are founded. The reader will presently see why I have brought Ångström's name prominently forward in connection with the interesting branch of spectroscopic analysis just referred to. If the discovery we are approaching had been effected by a tyro in the use of the spectroscope, doubts might very reasonably have been entertained respecting the exactness of the observations on which the discovery rests. It was suggested many years ago, long indeed before the true powers of spectroscopic analysis had been revealed, that perhaps if the light of the aurora were analyzed by the prism, evidence could be obtained of its electric nature. The eminent meteorologist Dove remarked, for instance, that the peculiarities presented by the electric light are so marked that it appears easy to decide definitely, by prismatic analysis, whether the light of the aurora is or is not electric. Singularly enough, however, the first proof that the auroral light is of an electric nature was derived from a very different mode of inquiry. Dr. Robinson of Armagh discovered in 1858, a year before Kirchhoff's recognition of the powers of spectroscopic analysis, that the light of the aurora possesses in a peculiar degree a property termed fluorescence, which is a recognized and characteristic property of the light produced by electrical discharges. These effects, he remarks, of the appearances presented by the auroral light under the tests he applied, were so strong in relation to the actual intensity of the light that they appear to afford an additional evidence of the electric origin of the phenomenon. Passing over this ingenious application of one of the most singular and interesting properties of light, we find that the earliest determination of the real nature of the auroral light, or rather of its spectrum, was that effected by Ångström. This observer took advantage of the occurrence of a brilliant aurora in the winter of 1867 to 1868 to analyze the spectrum of the colored streamers. A single bright line only was seen. Otto Struve, an eminent Russian astronomer, shortly afterwards made confirmatory observations. At the meeting of the Royal Astronomical Society in June 1868, Mr. Huggins thus described Struve's results. In a letter, Monsieur Otto Struve has informed me that he has had 2 good opportunities of observing the spectrum of the aurora borealis. The spectrum consists of one line, and the light is therefore monochromatic. The line falls near the margin of the yellow and green portions of the spectrum. This shows that the monochromatic light is greenish, which surprised me. But General Sabine tells me that in his polar expeditions he has frequently seen the aurora tinged with green, and this appearance corresponds with the position of the line seen by Monsieur Struve. The general import of this observation there is no mistaking. It teaches us that the light of the aurora is due to luminous vapor, and we may conclude, with every appearance of probability, that the luminosity of the vapor is due to the passage of electric discharges through it. It is, however, possible that the position of the bright line may be due to the character of the particles between which the discharges take place. But the view we are to take must depend upon the position of the line. Here a difficulty presents itself. There is no known terrestrial element whose spectrum has a bright line precisely in the position of the line in the auroral spectrum, and mere proximity has no significance whatever in spectroscopic analysis. Two elements differing as much from each other in character as iron and hydrogen may have lines so closely approximating in position that only the most powerful spectroscope can indicate the difference. So that when Ångström remarks that the bright line he has seen lies slightly to the left of a well-known group of lines belonging to the metal calcium, the principal ingredient of common chalk, we are by no means to infer that he supposes the substance which causes the presence of the bright line has any resemblance to that element. Until we can find an element which has a bright line in its spectrum absolutely coincident with the bright line detected by Ångström in the spectrum of the aurora, all speculation as to the real nature of the vapor in which the auroral electric discharge takes place, or of the substances between which the spark travels, is altogether precluded. It was supposed, after the total solar eclipse of 1869, that the spectrum of the sun's corona exhibited the same bright lines as the aurora. But recent observations show that the coincidence is not so close as it had been supposed, and, in fact, there is no evidence to show that the lines are the same. From Fraser's Magazine, February 1870. End of Section 2. Section 3 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Tyler Farmer. Light Science for Leisure Hours by Richard A. Proctor. The Earth a Magnet. There is a very prevalent but erroneous opinion that the magnetic needle points to the north. I remember well how I discovered in my boyhood that the needle does not point to the north, for the discovery was impressed upon me in a very unpleasant manner. I had purchased a pocket compass, and was very anxious, not indeed to test the instrument, since I placed implicit reliance upon its indications, but to make use of it as a guide across unknown regions. Not many miles from where I lived lay Cobham Wood, no very extensive forest certainly, but large enough to lose oneself in. Thither, accordingly, I proceeded with 3 schoolfellows. When we had lost ourselves, we gleefully called the compass into action, and made from the wood in a direction which we supposed would lead us home. We travelled on with full confidence in our pocket guide. At each turning we consulted it in an artistic manner, carefully poising it and waiting till its vibrations ceased. But when we had travelled some 2 or 3 miles without seeing any house or road that we recognized, matters assumed a less cheerful aspect. We were unwilling to compromise our dignity as explorers by asking the way, a proceeding which no precedent in history of our favorite travelers allowed us to think of. But evening came on, and with it a summer thunderstorm. We were getting thoroughly tired out, and the haec olim amice uabit with which we had been comforting ourselves began to lose its force. When at length we yielded, we learned that we had gone many miles out of our road, and we did not reach home till several hours after dark. Also, the offending compass was confiscated by justly indignant parents, so that for a long while the cause of our troubles was a mystery to us. In reality, instead of pointing due north, the compass pointed more than 20 degrees towards the west, or nearly to the quarter called by sailors north-northwest. No wonder, therefore, that we went astray when we followed a guide so untrustworthy. The peculiarity that the magnet needle does not, in general, point to the north, is the first of a series of peculiarities which I now propose briefly to describe. The irregularity is called by sailors the needle's variation, but the term more commonly used by scientific men is the declination of the needle. It was probably discovered a long time ago. For 800 years before our era, the Chinese applied the magnet's directive force to guide them in journeying over the great Asiatic plains, and they must soon have detected so marked a peculiarity. Instead of a ship's compass, they made use of a magnetic car, on the front of which a floating needle carried a small figure, whose outstretched arm pointed southwards. We have no record, however, of their discovery of the declination, and know only that they were acquainted with it in the 12th century. The declination was discovered independently by European observers in the 13th century. As we travel from place to place, the declination of the needle is found to vary. Christopher Columbus was the first to detect this. He discovered it on the 13th of September, 1492, during his first voyage, and when he was 600 miles from Faro, the most westerly of the Canary Islands. He found that the declination, which was towards the east in Europe, passed to the west, and increased continually as he traveled westwards. But here we see the first trace of a yet more singular peculiarity. I have said that at present the declination is towards the west in Europe. In Columbus's time, it was towards the east. Thus we learn that the declination varies with the progress of time, as well as with the change of place. The genius of modern science is a weighing and a measuring one. Men are not satisfied nowadays with knowing that a peculiarity exists. They seek to determine its extent, how far it is variable, whether from time to time or from place to place, and so on. Now the results of such inquiries applied to the magnetic declination have proved exceedingly interesting. We find, first, that the world may be divided into two unequal portions, over one of which the needle has a westerly and over the other an easterly declination. Along the boundary line, of course, the needle points due north. England is situated in the region of westerly magnets. This region includes all of Europe, except the northeastern parts of Russia, Turkey, Arabia, and the whole of Africa, the greater part of the Indian Ocean, and the western parts of Australia, nearly the whole of the Atlantic Ocean, Greenland, the eastern parts of Canada, and a small slice from the northeastern part of Brazil. All these form one region of westerly declination. But, singularly enough, there lies in the very heart of the remaining and larger region of easterly magnets an oval space of a contrary character. This space includes the Japanese islands, Manchuria, and the eastern parts of China. It is very noteworthy, also, that in the westerly region the declination is much greater than in the easterly. Over the whole of Asia, for instance, the needle points almost due north. On the contrary, in the north of Asia, for instance, the needle points almost due north. On the contrary, in the north of Greenland and of Baffin's Bay, the magnetic needle points due west, while still further to the north, a little westerly, we find the needle pointing with its north end directly towards the south. In the presence of these peculiarities, it would be pleasant to speculate. We might imagine the existence of powerfully magnetic veins in the Earth's solid mass, coercing the magnetic needle from a full obedience to the true polar summons. Or the comparative effects of oceans and of continents might be called into play. But unfortunately for all of this, we have to reconcile views founded on fixed relations presented by the Earth with the process of change indicated above. Let us consider the declination in England alone. In the 15th century, there was an easterly declination. This gradually diminished, so that in about the year 1657, the needle pointed due north. After this, the needle pointed towards the west, and continually more and more, so that scientific men, having had experience only of a continual shifting of the needle in one direction, began to form the opinion that this change would continue, so that the needle would pass through northwest and west to the south. In fact, it was imagined that the motion of the needle would resemble that of the hands of a watch, only in a reverse direction. But before long, observant men detected a gradual diminution in the needle's westerly motion. Arago, the distinguished French astronomer and physicist, was the first, I believe, to point out that the progressive movement of the magnetic needle towards the west appeared to have become continually slower of late years. He wrote in 1814, which seemed to indicate that after some little time longer it might become retrograde. 3 years later, namely on the 10th of February, 1817, Arago asserted definitively that the retrograde movement of the magnetic needle had commenced to be perceptible. Colonel Beaufoy at first oppugned Arago's conclusion, for he found from observations made in London during the years 1817 to 1819 that the westerly motion still continued. But he had omitted to take notice of the circumstance that London and Paris are two different places. A few years later, the retrograde motion became perceptible at London also, and has now been established by the observations of 40 years. It appears, from a careful comparison of Beaufoy's observations, that the needle reached the limit of its westerly digression at Greenwich in March of 1819, at which time the declination was very nearly 25 degrees. In Paris, on the contrary, the needle had reached its greatest western digression, about 22.5 degrees, in 1814. It is rather singular that although at Paris the retrograde motion thus presented itself 5 years earlier than in London, the needle pointed due north at Paris 6 years later than in London, viz., in 1663. Perhaps the greater amplitude of the needle's London digression may explain this peculiarity. It was already sufficiently difficult, says Arago, to imagine what could be the kind of change in the constitution of the globe which could act during 153 years in gradually transferring the direction of the magnetic needle from due north to 23 degrees west of north. We see that it is now necessary to explain, moreover, how it has happened that this gradual change has ceased, and has given place to a return toward the preceding state of the globe. How is it, he pertinently asks, that the directive action of the globe, which clearly must result from the action of molecules of which the globe is composed, can be thus variable, while the number, position, and temperature of these molecules, and, as far as we know, all their other physical properties, remain constant? But we may have considered only a single region of the earth's surface. Arago's opinion will seem still juster when we examine the change which has taken place in what we may term the magnetic aspect of the whole globe. The line which separates the region of westerly magnets from the region of easterly magnets now runs, as we have said, across Canada and eastern Brazil in one hemisphere, and across Russia, Asiatic Turkey, the Indian Ocean, and West Australia in the other, besides having an outline oval to the east of the Asiatic continent. These lines have swept round a part of the globe's circuit in a most singular manner since 1600. They have varied alike in direction and complexity. The Siberian oval, now distinct, was in 1787 merely a loop of the eastern line of no declination. The oval appears now to be continually diminishing, and will one day probably disappear. We find here presented to us a phenomenon as mysterious, as astonishing, and as worthy of careful study as any embraced in the wide domains of science. But other peculiarities await our notice. If a magnetic needle of suitable length be carefully poised on a fine point, or better, be suspended from a silk thread without torsion, it will be found to exhibit each day two small but clearly perceptible oscillations. Monsieur Arago, from a careful series of observations, deduced the following results. At about 11 at night, the north end of the needle begins to move from west to east, and having reached its greatest easterly excursion at about 8:15 in the morning, returns towards the west to attain its greatest westerly excursion at 1:15. It then moves again to the east, and having reached its greatest easterly excursion at 8:30 in the evening, returns to the west, and attains its greatest westerly excursion at 11 as at starting. Of course, these excursions take place on either side of the mean position of the needle, and as the excursions are small, never exceeding the 1/5 part of a degree, while the mean position of the needle lies some 20 degrees to the west of north, it is clear that the excursions are only nominally eastern and western, the needle pointing throughout far to the west. Now, if we remember that the north end of the needle is that furthest from the sun, it will be easy to trace in Monsieur Arago's results a sort of effort on the part of the needle to turn towards the sun, not merely when that luminary is above the horizon, but during his nocturnal path also. We are prepared, therefore, to expect that a variation having an annual period shall appear, on a close observation of our suspended needle. Such a variation has been long since recognized. It is found that in the summer of both hemispheres, the daily variation is exaggerated, while in winter it is diminished. But besides the divergence of a magnetized needle from the North Pole, there is a divergence from the horizontal position which must now claim our attention. If a non-magnetic needle be carefully suspended so as to rest horizontally and be then magnetized, it will be found no longer to preserve that position. The northern end dips very sensibly. This happens in our hemisphere. In the southern, it is the southern end which dips. It is clear, therefore, that if we travel from one hemisphere to the other, we must find the northern dip of the needle gradually diminishing, till at some point near the equator the needle is horizontal, and as we pass thence to southern regions, a gradually increasing southern incline is presented. This has been found to be the case, and the position of the line which there is no inclination, called the magnetic equator, has been traced around the globe. It is not coincident with the Earth's equator, but crosses that circle at an angle of 12 degrees, passing from north to south of the equator in long, 3 degrees west of Greenwich, and from south to north in long, 187 degrees east of Greenwich. The form of the line is not exactly that of a great circle, but presents here and there, and especially where it crosses the Atlantic, perceptible excursions from such a figure. At 2 main points on the Earth's globe, the needle will rest in a vertical position. These are the magnetic poles of the Earth. The northern magnetic pole was reached by Sir J. G. Ross and lies in 7 degrees north latitude and 206 degrees east longitude, that is, to the north of the American continent, and not very far from Boothia Gulf. One of the objects with which Ross set out on his celebrated expedition to the Antarctic seas was the discovery, if possible, of the southern magnetic pole. In this he was not successful. Twice he was in hopes of attaining his object, but each time he was stopped by a barrier of land. He approached so near, however, to the pole, that the needle was inclined at an angle of nearly 90 degrees to the horizon, and he was able to assign to the southern pole a position in 75 degrees southern latitude, 154 degrees east longitude. It is not probable, we should imagine, that either pole is fixed, since we shall now see that the inclination, like the declination of the magnetic needle, is variable from time to time, as well as from place to place, and in particular, the magnetic equator is apparently subjected to a slow but uniform process of change. Arago tells us that the inclination of the needle at Paris has been observed to diminish year by year since 1671. At that time, the inclination was no less than 75 degrees. In other words, the needle was inclined only 50 degrees to the vertical. In 1791, the inclination was less than 71 degrees. In 1831, it was less than 68 degrees. In like manner, the inclination at London has been observed to diminish, from 72 degrees in 1786 to 70 degrees in 1804, and thence to 68 degrees at the present time. It might be anticipated from such changes as these that the magnetic equator would be found to be changing in position. Nay, we can even guess in which way it must be changing. For since the inclination is diminishing at London and Paris, the magnetic equator must be approaching these places, and this, in the present position of the curve, can only happen by a gradual shifting of the magnetic equator from east to west along the true equator. This motion has been found to be really taking place. It is supposed that the movement is accompanied by a change of form, but more observations are necessary to establish this interesting point. Can it be doubted that while these changes are taking place, the magnetic poles also are slowly shifting around the new pole? Must not the northern pole, for instance, be further from Paris now that the needle is inclined more than 23 degrees from the vertical than in 1671, when the inclination was only 15 degrees? It appears obvious that this must be so, and we deduce the interesting conclusion that each of the magnetic poles is rotating around the Earth's axis. But there is another peculiarity of the needle, which is as noteworthy as any of those I have mentioned. I refer to the intensity of the magnetic action, the energy with which the needle seeks its position of rest. This is not only variable from place to place, but from time to time, and is further subject to sudden changes of a very singular character. It might be expected that where the dip is greater, the directive energy of the magnet will be proportionally great, and this is found to be approximately the case. Accordingly, the magnetic equator is very nearly coincident with the equator of least intensity, but not exactly. As we approach the magnetic poles, we find a more considerable divergence, so that instead of there being a northern pole of greatest intensity nearly coincident with the northern magnetic pole, which we have seen lies to the north of the American continent, there are two northern poles, one in Siberia, nearly at the point where the river Lena crosses the Arctic Circle, the other not so far to the north, only a few degrees north, in fact, of Lake Superior. In the south, in like manner, there are also two poles, one of the Antarctic Circle, about 130 degrees east longitude, in Adélie Land, the other not yet precisely determined, but supposed to lie on about the 240th degree of longitude, and south of the Antarctic Circle. Singularly enough, there is a line of lower intensity running right round the earth along the valleys of the two great oceans, passing through Bering Straits and bisecting the Pacific on one side of the globe, and passing out of the Arctic Sea by Spitzbergen and down the Atlantic on the other. Colonel Sabine discovered that the intensity of the magnetic action varies during the course of the year. It is greatest in December and January in both hemispheres. If the intensity had been greatest in winter, one would have been disposed to have assigned seasonal variation of temperature as the cause of the change. But as the epoch is the same for both hemispheres, we must seek another cause. Is there any astronomical element which seems to correspond with the law discovered by Sabine? There is one very important element. The position of the perihelion of the Earth's orbit is such that the Earth is nearest to the Sun on about the 31st of December or the 1st of January. There seems nothing rashly speculative, then, in concluding that the Sun exercises a magnetic influence on the Earth, varying accordingly to the distance of the Earth from the Sun. Nay, Sabine's results seem to point very distinctly to the law of variation. For, although the number of observations is not as yet very great, and the extreme delicacy of the variation renders the determination of its amount very difficult, enough has been done to show that in all probability the Sun's influence varies according to the same law as gravity, that is, inversely as the square of the distance. That the Sun, the source of light and heat, and the great gravitating center of the solar system, should exercise a magnetic influence upon the Earth, and that this influence should vary according to the same law as gravity, or as the distribution of light and heat, will not appear perhaps very surprising. But the discovery by Sabine that the moon exercises a distinctly traceable effect upon the magnetic needle seems to me a very remarkable one. We receive very little light from the moon, much less, in comparison with the sun's light, than most persons would suppose, and we get absolutely no perceptible heat from her. Therefore, it would seem rather to the influence of mass and proximity that the magnetic disturbances caused by the moon must be ascribed. But if the moon exercises an influence in this way, why should not the planets? We shall see that there is evidence of some influence being exerted by these bodies. More mysterious, if possible, than any of the facts I have discussed is the phenomenon of magnetic storms. The needle has been exhibiting for several weeks the most perfect uniformity of oscillation. Day after day, the careful microscopic observation of the needle's progress has revealed a steady swaying to and fro, such as may be seen in the masts of a stately ship at anchor on the scarce heaving breast of ocean. Suddenly a change is noted. Irregular jerking movements are perceptible, totally distinct from the regular periodic oscillations. A magnetic storm is in progress. But where is the center of disturbance, and what are the limits of the storm? The answer is remarkable. If the jerking movements observed in places spread over very large regions of the earth, and in some well-authenticated cases over the whole earth, be compared with the local time, it is found that, allowance being made for difference of longitude, they occur precisely at the same instant. The magnetic vibrations thrill in one moment through the whole frame of our earth. But a very singular circumstance is observed to characterize these magnetic storms. They are nearly always observed to be accompanied by the exhibition of the aurora in high altitudes northern and southern. Probably they never happen without such a display, but numbers of auroras escape our notice. The converse proposition, however, has been established as a universal one. No great display of the aurora ever occurs without a strongly marked magnetic storm. Magnetic storms sometimes last for several hours or even days. Remembering the influence which the sun has been found to exercise upon the magnetic needle, the question will naturally arise: has the sun anything to do with magnetic storms? We have clear evidence that he has. On the 1st of September, 1859, Messrs. Carrington and Hodgson were observing the sun, one at Oxford and the other in London. Their scrutiny was directed to certain large spots which, at that time, marked the sun's face. Suddenly, a bright light was seen by each observer to break out on the sun's surface, and to travel, slowly in appearance but in reality at the rate of about 7,000 miles in a minute, across a part of the solar disk. Now, it was found afterwards that the self-registering magnetic instruments at Q had made at that very instant a strongly marked jerk. We learned also that at that moment a magnetic storm prevailed at the West Indies, in South America, and in Australia. The signalmen in the telegraph stations at Washington and Philadelphia received strong electric shocks. The pen of Bain's telegraph was followed by a flame of fire, and in Norway the telegraphic machinery was set on fire. At night, great auroras were seen in both hemispheres. It is impossible not to connect these startling magnetic indications with the remarkable appearance observed upon the sun's disk. But there is other evidence. Magnetic storms prevail more commonly in some years than in others. In those years in which they occur most frequently, it is found that the ordinary oscillations of the magnetic needle are more extensive than usual. Now, when these peculiarities had been noticed for many years, it was found that there was an alternate and systematic increase and diminution in the intensity of magnetic action, and that the period of the variation was about 11 years. But at the same time, a diligent observer had been recording the appearance of the sun's face from day to day and from year to year. He had found that the solar spots are in some years more freely displayed than in others. And he had determined the period in which the spots are successively presented with maximum frequency to be about 11 years. On a comparison of the two sets of observations, it was found, and has now been placed beyond a doubt by many years of continued observation, that magnetic perturbations are most energetic when the sun is most spotted, and vice versa. For so remarkable a phenomenon as this, none but a cosmical cause can suffice. We can neither say that the spots cause the magnetic storms, nor that the magnetic storms cause the spots. We must seek for a cause producing at once both sets of phenomena. There is, as of yet, no certainty in this matter, but it seems as if philosophers would soon be able to trace in the disturbing action of the planets upon the solar atmosphere the cause as well of the marked period of 11 years as of other less distinctly marked periods which a diligent observation of solar phenomena is beginning to educe. From the Cornhill Magazine, June 1868. End of section 3.
Section 4 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melissa Jean. Light Science for Leisure Hours by Richard A. Proctor. Our Chief Timepiece, Losing Time. A distinguished French astronomer, author of one of the most fascinating works on popular astronomy that has hitherto appeared, remarks that a man would be looked upon as a maniac who should speak of the influence of Jupiter's moons upon the cotton trade. Yet, as he proceeds to show, there is an easily traced connection between the ideas which appear at first so incongruous. The link is found in the determination of celestial longitude. Similarly, we should be disposed to wonder at an astronomer who, regarding thoughtfully the stately motion of the sidereal system as exhibited on a magnified and therefore appreciable scale by a powerful telescope, should speak of the connection between this movement and the intrinsic worth of a sovereign. The natural thought with most men would be that too much learning had made the astronomer mad. Yet when we come to inquire closely into the question of a sovereign's intrinsic value, we find ourselves led to the diurnal motion of the stars, and that by no very intricate path. For what is a sovereign? A coin containing so many grains of gold mixed with so many grains of alloy. A grain, we know, is the weight of such and such a volume of a certain standard substance. that is, so many cubic inches, or parts of a cubic inch of that substance. But what is an inch? It is determined, we find, as a certain fraction of the length of a pendulum vibrating seconds in the latitude of London. A second, we know, is a certain portion of a mean solar day, and is practically determined by a reference to what is called the sidereal day. The interval, namely between the successive passages by the same star of the celestial meridian of any fixed place. This interval is assumed to be constant, and it has, indeed, been described as the one constant element known to astronomers. We find then that there is a connection, and a very important connection, between the motion of the stars and our measures, not merely of value, but of weight, length, volume, and time. In fact, our whole system of weights and measures is found on the apparent diurnal motion of the sidereal system, that is, on the real diurnal rotation of the earth. We may look on the meridian plane, in which the great transit telescope of the Greenwich Observatory is made to swing, as the gigantic hand of a mighty dial, a hand which, extending outwards among the stars, traces out for us, by its motion among them, the exact progress of time, and so gives us the means of weighing, measuring, and valuing terrestrial objects, with an exactitude which is at present beyond our wants. The earth, then, is our chief timepiece, and it is of the correctness of this giant clock that I am now to speak. But how can we test a timepiece whose motions we select to regulate every other timepiece? If a man sets his watch every morning by the clock at Westminster, it is clearly impossible for him to test the accuracy of that clock by the motions of his watch. It would, indeed, be possible to detect any gross change of rate, but for the purpose of illustration, I assume, what is indeed the case, that the clock is very accurate, and therefore that minute errors only are to be looked for even in the long intervals of time. And just as the watch set by a clock cannot be made use of to test the clock for small errors, so our best timepieces cannot be employed to detect slow variations, if any such exist, in the earth's rotation period. Sir William Herschel, who early saw the importance of the subject, suggested another method. Some of the planets rotate in such manner, and bear such distinct marks upon their surface, that it is possible, by a series of observations extending over a long interval of time, to determine the length of their rotation period within a second or two. Supposing their rotation uniform, we obtain at once an accurate measure of time. Supposing their rotation not uniform, we obtain 1. A hint of the kind of change we are looking for, and 2. By the comparison of two or more planets, the means of guessing how the variation is to be distributed between the observed planets and our Earth. Unfortunately, it turned out that Jupiter, one of the planets from which Herschel expected most, does not afford us exact information, his real surface being always veiled by his dense and vapor-laden atmosphere. Saturn, Venus, and Mercury are similarly constructed, and are in other respects unfavourable objects for this sort of observation. Mars only, of all the planets, is really available. Distinctly marked, in telescopes of sufficient power, with continents and oceans which are rarely concealed by vapours, this planet is in other respects fortunately situated, for it is certain that whatever variations may be taking place in planetary rotations must be due to external agencies. Now Saturn and Jupiter have their satellites to influence, perhaps appreciably in long intervals of time, their rotation movements. Venus and Mercury are near the Sun, and are therefore in this respect worse off than the Earth, whose rotation is in question. Mars, on the other hand, farther removed than we are from the Sun, having also no moon, and being of small dimensions, a very important point be it observed, since the tidal action of the Sun depends on the dimensions of a planet, is likely to have a rotation period all but absolutely constant. Herschel was rather unfortunate in his observations of Mars. Having obtained a rough approximation from Mars's rotational an interval of 2 days, this rough approximation being, as it chanced, only 37 seconds in excess of the true period, he proceeded to take 3 intervals of 1 month each. This should have given a much better value, but as it happened, the mean of the values he obtained was 46 seconds too great. He then took a period of 2 years, and being misled by the erroneous values he had already obtained, he missed 1 rotation, getting a value 2 minutes too great. 30 years ago, 2 German astronomers, Weir and Madler, tried the same problem, and taking a period of 7 years, obtained a value which exceeds the true value by only 1 second. Another German, Kaiser, by combining more observations, obtained a value which is within 1/15th of a second of the true value. But a comparison of observations extending over 200 years has enabled me to obtain a value which I consider to lie within 1/100th part of a second of the truth. This value for Mars's rotation period is 24 hours, 37 minutes, 22 seconds, and 73 milliseconds. Here then we have a result so accurate that at some future time it may serve to test the Earth's rotation period. We have compared the rotation rate of our test planet with the Earth's rate during the past 200 years, and therefore, if the Earth's rate varies by more than 1/100th of a second in the next 200 or 300 years, we shall, or rather our descendants will, begin to have some notion of the changes at the end of that time. But in the meantime, mankind being impatient, and not willing to leave to a distant posterity any question which can possibly be answered now, astronomers have looked around them for information available at once on this interesting point. The search has not been in vain. In fact, we were able to announce, with an approach to positiveness, that our great terrestrial timepiece is actually losing time. In our moon we have a neighbor which has long been in the habit of answering truthfully questions addressed to her by astronomers. Of old she told Newton about gravitation, and when he doubted and urged opposing evidence offered, as men in his time supposed, by the earth, she set him on the right track. So that when in due time the evidence offered by the earth was corrected, Newton was prepared at once to accept and propound the noble theory which rendered his name illustrious. Again, men wished to learn the true shape of the earth, and went hither and thither measuring its globe, but the moon, meanwhile, told the astronomer who remained at home a truer tale. They sought to learn the earth's distance from the sun, and from this and that point they turned their telescopes on Venus in transit, but the moon set them nearer the truth, and that not by a few miles, but by 2,000,000 miles or more. We shall see that she has had something to say about our great terrestrial timepiece. One of the great charms of the science of astronomy is, that it enables men to predict. At such and such an hour, the astronomer is able to say, a celestial body will occupy such and such a point on the celestial sphere. You direct a telescope towards the point named, and lo, at the given instant, the promised orb sweeps across the field of view. Each year there is issued a thick octavo volume crowded with such predictions, 3 or 4 years in advance of the events predicted, and these predictions are accepted with as little doubt by astronomers as if they were the records of past events. But astronomers are not only able to predict, they can also trace back the paths of celestial bodies, and say, at such and such a long past epoch, a given star or planet occupied such and such position upon the celestial sphere. But how are they to verify such a statement? It is clear that, in general, they cannot do so. Those who are able to appreciate, or better, to make use of, the predictions of astronomy, will indeed very readily accord a full measure of confidence to calculations of past events. They know that astronomy is justly named the most exact of sciences, and they can see that there is nothing, in the nature of things, to render retrospection more difficult than prevision. But there are hundreds who have no such experience of the exactness of modern astronomical methods, who have, on the contrary, a vague notion that modern astronomy is merely the successor of systems now exploded, perhaps even that it may one day have to make its way in its turn for new methods. And if all other men were willing to accept the calculations of astronomers respecting long past events, astronomers themselves would be less easily satisfied. Long experience has taught them that the detection of error is the most fruitful source of knowledge. Therefore, wherever such a course is possible, they always gladly submit their calculations to the test of observation. Now, looking backward into the far past, it is only here and there that we see records which afford means of comparison with modern calculations. The planets had swept on their courses for ages, with none to note them. Gradually, observant men began to take notice and record the more remarkable phenomena, but such records, made with very insignificant instrumental means, had in general but little actual value. It has been found easy to confirm them without any special regard to accuracy of calculation. There is one class of phenomena, however, which no inaccuracy of observation can very greatly affect. A total eclipse of the sun is an occurrence so remarkable that 1. It can hardly take place without being recorded, and 2. A very rough record will suffice to determine the particular eclipse referred to. Long intervals elapse between successive total eclipses visible at the same place on the earth's surface, and even partial eclipses of noteworthy extent occur but seldom at any assigned place. Very early, therefore, in the history of modern astronomy, the suggestion was made that eclipses recorded by ancient historians should be calculated retrospectively. An unexpected result rewarded the undertaking. It was found that ancient eclipses could not be fairly accounted for without assigning a slower motion to the moon in long past ages than she has at present. Here was a difficulty which long puzzled mathematicians. One after another was foiled by it. Halley, an English mathematician, had detected the difficulty, but no English mathematician was able to grapple with it. Contented with Newton's fame, they had suffered their continental rivals to shoot far ahead in the course he had pointed out. But the best continental mathematicians were defeated. In papers of acknowledged merit, adorned by a variety of new processes, and showing a deep insight into the question at issue, they yet arrived, one and all, at the same conclusion: failure. 90 years elapsed before the true explanation was offered by the great mathematician Laplace. A full exposition of his views would be out of place in such a paper as the present, but briefly they amount to this. The moon travels in her orbit, swayed chiefly by the earth's attraction, but the sun, though greatly more distant, yet owing to the immensity of his mass, plays an important part in guiding our satellite. His influence tends to relieve the moon in part from the earth's sway. Thus she travels in a wider orbit, and with a slower motion, than she would have but for the sun's influence. Now the earth is not at all times equally distant from the sun, and his influence upon the moon is accordingly variable. In winter, when the earth is nearest to the sun, his influence is greatest. The lunar month, accordingly, though the difference is very slight, is longer in winter than in summer. This variation has long been recognized as the moon's annual equation, but Laplace was the first to point out that the variation is itself slowly varying. The earth's orbit is slowly changing in shape, becoming more and more nearly circular year by year. As the greater axis of her orbit is unchanging, it is clear that the actual extent of the orbit is slowly increasing. Thus the moon is slightly released from the sun's influence year by year, and so brought more and more under Earth's influence. She travels therefore continually faster, though the change is indeed but a very minute one, only to be detected in long intervals of time. Also the moon's acceleration, as the change is termed, is only temporary, and will in due time be replaced by an equally gradual retardation. When Laplace had calculated the extent of the change due to the cause he had detected, and when it was found that ancient eclipses were now satisfactorily accounted for, it may well be believed that there was triumph in the mathematical camp. But this was not all. Other mathematicians attacked the same problem, and their results agreed so closely that all were convinced that the difficulty was thoroughly vanquished. A very noteworthy result followed from Laplace's calculations. Amongst other solutions which had been suggested was the supposition, supported by no less an authority than Sir Isaac Newton, who lived to see the commencement of the long conflict maintained by mathematicians with this difficulty, that it is not the moon travelling more quickly, but our earth rotating more slowly, which causes the observed discrepancy. Now, it resulted from Laplace's labours, as he was the first to announce, that the period of the earth's rotation had not varied by 1/10 of a second per century in the last 2,000 years. The question thus satisfactorily settled, as was supposed, was shelved for more than a quarter of a century. The result also, which seemed to flow from the discussion, the constancy of the earth's rotation movement, was accepted, and, as we have seen, our national system of measures was founded upon the assumed constancy of the day's duration. But mathematicians were premature in their rejoicings. The question had been brought by the labours of Professor Adams, a co-discoverer with Leverrier of the distant Neptune, almost exactly to the point which it occupied a century ago. We are face to face with the very difficulties, somewhat modified in extent, but not in character, which puzzled Halley, Euler, and Lagrange. It would be an injustice to the memory of Laplace to say that his labours were thrown away. The explanation offered by him is indeed a just one, but it is insufficient. Properly estimated, it removes only half the difficulty which had perplexed mathematicians. It would be quite impossible to present in brief space, and in form suited to these pages, the views propounded by Adams. What, for instance, would most of our readers learn if we were to tell them that, when the variability of the eccentricity is taken into account in integrating the differential equations involved in the problem of lunar motions, that is, when the eccentricity is made a function of the time, non-periodic or secular terms appear in the expression for the moon's mean motion, and so on. Let it suffice to say that Laplace had considered only the work of the sun in diminishing the earth's pull on the moon. Supposing that the slow variation in the sun's direct influence on the moon's motion in her orbit must be self-compensatory in long intervals of time. Adams had shown, on the contrary, that when this variation is closely examined, no such compensation is found to take place, and that the effect of this want of compensation is to diminish by more than one-half the effects due to the slow variation examined by Laplace. These views gave rise, at first, to considerable controversy. Pontécoulant characterized Adam's processes as analytical conjuring tricks, and Leverrier stood up gallantly in defense of Laplace. The contest swayed hither and thither for a while, but gradually the press of new arrivals on Adam's side began to prevail. One by one his antagonists gave way. New processes have confirmed his results, figure for figure, and no doubt now exists in the minds of any astronomer competent to judge of the correctness of Adam's views. But side by side with this inquiry, another had been in progress. A crowd of diligent labourers had been searching with close and rigid scrutiny into the circumstances attending ancient eclipses. A new light had been thrown upon this subject by the labours of modern travellers and historians. One remarkable instance of this may be cited. Mr. Layard has identified the site of Larissa with the modern Nimrod. Now Xenophon relates that when Larissa was besieged by the Persians, an eclipse of the sun took place, so remarkable in its effects, and therefore undoubtedly total, that the Median defenders of the town threw down their arms, and the city was accordingly captured. And Hansen has shown that a certain estimate of the moon's motion makes the eclipse which occurred on August 15th, 310 BC, not only total, but central at Nimrod. Some other remarkable eclipses, as the celebrated sunset eclipse total at Rome 399 BC, the eclipse which enveloped the fleet of Agathocles as he escaped from Syracuse, the famous eclipse of the Thales, which interrupted a battle between the Medes and the Lydians, and even the partial eclipse which possibly caused the going back of the shadow upon the dial of Az, have all been accounted for satisfactorily by Hansen's estimate of the moon's motion. So also have 19 lunar eclipses recorded in the Almagest. This estimate of Hansen's, which accounts so satisfactorily for solar and lunar eclipses, makes the moon's rate of motion increase more than twice as fast as it should do, according to the calculations of Adams. But before our readers run away with the notion that astronomers have here gone quite astray, it will be well to present, in a simple manner, the extreme minuteness of the discrepancy about which all the coil has been made. Suppose that just in front of our moon, a false moon, exactly equal to ours in size and appearance, were set off with a motion corresponding to the present motion of the moon, save only in one respect, namely, that the false moon's motion should not be subject to the change we are considering, termed the acceleration. Then 100 years would elapse before our moon would fairly begin to show in advance. She would in that time have brought only 1/150th part of her breadth from behind the false moon. At the end of another century she would have gained 4 times as much, at the end of a third 9 times as much, and so on. She would not fairly have cleared her own breadth in less than 1200 years. But the whole of this gain, minute as it is not left unaccounted for by our modern astronomical theories. Half the gain is explained, the other half remains to be interpreted. In other words, the moon travels further by about half her own breadth in 12 centuries than she should do according to the lunar theory. But in this difficulty, small as it seems, we are not left wholly without resource. We are not only able to say that the discrepancy is probably due to a gradual retardation of the Earth's rotation movement, but we are able to place our finger on a very sufficient cause for such a retardation. One of the most firmly established principles of modern science is this, that where work is done, force is, in some way or other, expended. The doing of work may show itself in a variety of ways. In the generation of heat, in the production of light, in the raising of weights, and so on, but in every case an equivalent force must be expended. If the brakes are applied to a train in motion, intense heat is generated in the substance of the brake. Now the force employed by the brakesman is not equivalent to the heat generated. Where, then, is the balance of force expended? We all know that the train's motion is retarded, and this loss of motion represents the requisite expenditure of force. Now, is there any process in nature resembling, in however remote a degree, the application of a brake to check the earth's rotation? There is. The tidal wave which sweeps twice a day round the earth travels in a direction contrary to the earth's motion of rotation. That this wave does work, no one can doubt who has watched its effects. The mere rise and fall in open ocean may not be strikingly indicative of work done, But when we see the behavior of the tidal wave in narrow channels, when we see heavily laden ships swept steadily up our tidal rivers, we cannot but recognize the expenditure of force. Now, where does this force come from? Motion being the great force measurer, what motion suffers that the tides may work? We may securely reply that the only motion which can supply the requisite force is the earth's motion of rotation. Therefore it is no mere fancy, but a matter of absolute certainty, that, though slowly, still very surely, our terrestrial globe is losing its rotation movement. Considered as a timepiece, what are the earth's errors? Suppose for a moment that the earth was timed and rated 2,000 years ago. How much has she lost, and what is her rate error? She has lost in that interval nearly 1 hour and a quarter, and she is losing now at the rate of 1 second in 12 weeks. In other words, the length of a day is now more by about 1/84th part of a second than it was 2,000 years ago. At this rate of change, our day would merge into a lunar month in the course of 36 millions of years. But after a while, the change will take place more slowly, and some trillion or so years will elapse before the full change is effected. Distant, however, as is the epoch at which the changes we have been considering will become effective, the subject appears to us to have an interest apart from the mere speculative consideration of the future physical condition of our globe. Instead of the recurrence of ever-varying, closely intermingled cycles of fluctuation, we see now for the first time the evidence of cosmical decay, a decay which, in its slow progress, may be but the preparation for a new genesis, but still a decay which, so far as the races at present subsisting upon the earth are concerned, must be looked upon as finally and completely destructive. From Chambers' Journal, October 12, 1867. End of section 4.
Section 5 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Ashley M. Light Science for Leisure Hours by Richard A. Proctor. Encke the Astronomer. The years which have passed since Encke died have witnessed notable changes in the aspect of the science he loved so well. But we must look back over more than half a century if we would form an estimate of the position of astronomy when Encke's most notable work was achieved. At Seeberge, under Lindenau, Encke had been perfecting himself in the higher branches of mathematical calculation. He took the difficult work of determining the orbital motions of newly discovered comets under his special charge, and Dr. Bruns tells us that every comet which was detected during Encke's stay at Seeberge was subjected to rigid scrutiny by the indefatigable mathematician. Before long, a discovery of the utmost importance rewarded his persevering labors. Pons had detected, on November 26, 1818, a comet of no very brilliant aspect, which was watched first at Marseilles and then at Mannheim until December 29. Encke next took up the work, and tracked the comet until January 12. Combining the observations made between December 22 and January 12, he assigned to the body a parabolic orbit. But he was not satisfied with the accordance between the path and the observed motions of the body. When he attempted to account for the motions of the comet by means of an orbit of comparatively short period, he was struck by the resemblance between the path thus deduced and that of Comet 1, 1805. Gradually the idea dawned upon him that a new era was opening for science. Hitherto the only periodical comets which had been discovered except Lexell's, the lost comet, had travelled in orbits extending far out into space beyond the paths of the most distant known planets. But now Encke saw reason to believe that he had to deal with a comet travelling within orbit of Jupiter. On February 5th he wrote to the eminent mathematician Gauss, pointing out the results of his inquiries, and saying that he only waited for the encouragement and authority of his former teacher to prosecute his researches to the end toward which they already seemed to point. Gauss, in reply, not only encouraged Encke to proceed, but counselled him as to the course he should pursue. The results we all know. Encke showed conclusively that the newly discovered comet travels in a path of short period, and that it had already made an appearance several times in our neighborhood. From the date of this discovery, Encke took high rank among the astronomers of Europe. His subsequent labors by no means fell short of the promise which this, his first notable achievement, had afforded. If he effected less as an astronomical observer than many of his contemporaries, he was surpassed by few as a manipulator of those abstruse formulae by which the planetary perturbations are calculated. It was to the confidence engendered by this skill that we owe his celebrated discovery of the acceleration of the motion of the comet mentioned above. Assured that he had rightly estimated the disturbances to which the comet is subjected, he was able to pronounce confidently that some cause continually, though all but imperceptibly, impedes the passage of this body through space, and so, by one of those strange relations which the student of astronomy is familiar with, the continually retarded comet travels ever more swiftly along continually diminishing orbit. Braun's Life of Encke is well worth reading, not only by those who are interested in Encke's fame and work as an astronomer, but by the general reader. Encke the man is presented to our view, as well as Encke the astronomer. With loving pains, the pupil of the great astronomer handles the theme he has selected. The boyhood of Encke, his studies, his soldier life in the great uprising against Napoleon in 1813, and his work at the Seeberge Observatory, his labors on comets and asteroids, his investigations of the transits of 1761 and 1769, his life as an academician and as director of an important observatory, his orations at festival and funeral, and lastly his illness and death, are described in these pages by one who held Encke in grateful remembrance as teacher and master, and as a fatherly friend. Not the least interesting feature of the work is the correspondence introduced into its pages. We find Encke in communication with Humboldt, with Bessel and Struve, with Hansen, Olbers, and Argelander, with the host, in fine, of living as well as of departed men of science. From Nature, March 10, 1870. End of Section 5. Recording by Ashley M.
Section 6 of Light Science for Leisure Hours. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a recording by Joanne Crosby. Light Science for Leisure Hours by Richard A. Proctor. Venus on the Sun's Face. More than a century ago, scientific men were looking forward with eager interest to the passage of the planet Venus across the Sun's face in 1769. The Royal Society judged the approaching event to be of such extreme importance to the science of astronomy that they presented a memorial to King George III, requesting that a vessel might be fitted out, at government expense, to convey skillful observers to one of the stations which had been judged suitable for observing the phenomenon. The petition was complied with, and after some difficulty as to the choice of a leader, the good ship Endeavour of 370 tons was placed under the command of Captain Cook. The astronomical work entrusted to the expedition was completely successful, and thus it was held that England had satisfactorily discharged her part of the work of utilizing the rare phenomenon known as a transit of Venus. A century passed, and science was again awaiting with interest the approach of one of these transits. But now her demands were enlarged. It was not one ship that was asked for, but the full cost and charge of several expeditions. And this time, also, science had been more careful in taking time by the forelock. The first hints of her requirements were held some 14 years ago, when the Astronomer Royal began that process of laboriously inquiring which a question of this sort necessarily demands. Gradually her hints became more and more plain-spoken, insomuch that Airy, her mouthpiece in this case, stated definitely in 1868 what he thought science had a right to claim from England in this matter. When the claim came before our government, it was met with a liberality which was a pleasing surprise after some former placid reference of scientific people to their own devices. The sum of £10,500 was granted to meet the cost of several important and well-appointed expenditures, and further material aid was derived from the various government observatories. And now let us inquire why so much interest is attached to a phenomenon which appears at first to be so insignificant. Transit eclipses and other phenomena of that nature are continually occurring, without any particular interest being attached to them. The telescopist may see half a dozen such phenomena in the course of a night or two by simply watching the satellites of Jupiter or the passage of our moon over the stars. Even the great eclipse of 1868 did not attract so much interest as the transit of Venus. Yet that eclipse had not been equaled in importance by any which has occurred in historic times, and hundreds of years must pass before such another happens, whereas transits of Venus are far from being so uncommon. The fact is that Venus gives us the best means we have of mastering a problem which is one of the most important within the whole range of the science of astronomy. I use the term important, of course, with reference to the scientific significance and interest of the problem. Practically, it matters little to us whether the sun is 1,000,000 of miles or thousands of miles from us. The object must in any case be looked upon as an extraparochial one. But science does occasionally attach immense interest to extraparochial subjects, and this is neither unwise nor unreasonable, since we find implanted in our own very nature, and not merely in the nature of scientific men, a quality which causes us to take interest in a variety of matters that do not in the least concern our personal interests. Nor is this quality rather considered one of the least noble characteristics of the human race. That the determination of the sun's distance is important, in an astronomical sense, will be seen at once when it is remembered that the ideas we form of the dimensions of the solar system are wholly dependent on our estimate of the sun's distance. Nor can we gauge the celestial depths with any feeling of assurance, unless we know the true length of that which is our sole measuring rod. It is, in fact, our basis of measurement for the whole visible universe. In some respects, even if we knew the sun's distance exactly, it would still be an unsatisfactory gauge for the stellar depths. But that is the misfortune, not the fault, of the astronomer, who must be content to use the measuring rod which nature gives him. All he can do is to find out as nearly as possible its true length. When we come to consider how the astronomer is to determine this very element, the sun's distance, we find that he is hampered with a difficulty of precisely the same character. The sun being an inaccessible object, the astronomer can apply no other methods to determine its distance directly than those which a surveyor would use in determining the distance of an inaccessible castle, or rock, or tree, or the like. We shall see presently that the ingenuity of astronomers has, in fact, suggested some other indirect methods. But clearly the most satisfactory estimate we can have of the sun's distance is one founded on some simple notations and involving the main such processes of calculations as we have to deal with in ordinary surveying. There is, in this respect, no mystery about the solution of the famous problem. Unfortunately, there is an enormous difficulty. When a surveyor has to determine the distance of an inaccessible object, he proceeds in the following manner. He first very carefully measures a baseline of convenient length. Then from either end of the baseline, he takes the bearing of the inaccessible object. That is, he observes the direction in which it lies. It is clear that, if he were to now draw a figure on paper, laying down the baseline to some convenient scale, and drawing lines from its end in direction corresponding to the bearings of the observed object, these lines would indicate, by their intersection, the true relative position of the object. In practice, the mathematician does not trust to so rough a method as construction, but applies processes of calculation. Now it is clear that in this plan everything depends on the baseline. It must not be too short in comparison with the distance of the inaccessible object, for then, if we make the least error in observing the bearings of the object, we get an important error in the resulting determination of the distance. The reader can easily convince himself of this by drawing an illustrative case or two on paper. The astronomer has to take his baseline for determining the sun's distance upon our Earth, which is quite a tiny speck in comparison with the vast distance which separates us from the sun. It has been found difficult enough to determine the moon's distance with such a short baseline to work from. But the moon is only about 250,000 of miles from us, while the sun is more than 90 millions of miles off. Thus the problem was made several times more difficult, or to speak more correctly, it was rendered simply insoluble, unless the astronomer could devise some mode of observing which should vastly enhance the power of his instruments. For let us consider an illustrative case. Suppose there was a steeple 5 miles off, and we had a baseline only 2 feet long. That would correspond as nearly as possible to the case of the astronomer has to deal with. Now, what change of direction could be observed in the steeple by merely shifting the eye along a line of 2 feet? There is a ready way of answering. Invert the matter. Consider that a line of 2 feet long would look like if viewed from a distance of 5 miles. Would its length be appreciable? To say nothing of being measurable? Yet it is just such a problem as the measurement of that line which the astronomer would have to solve. But even this is not all. In our illustration, only one observer is concerned, and he would be able to use one set of instruments. Suppose, however, that from one end of the 2-foot line, an observer using one set of instruments took the bearings of the steeple, and that half a year after, another observer brought another set of instruments and took the bearing of the steeple from the other end of the 2-foot line. Is it not obvious how enormously the uncertainty of the results would be increased by such an arrangement as this? One observer would have his own peculiar powers of observation, his own peculiar weaknesses. The other would have different peculiarities. One set of instruments would be characterized by its own faults or merits, so would the other. One series of observations would be made in summer, with all the disturbing effects due to heat. The other would be made in winter, with all the disturbing effects due to cold. The observation of the sun is characterized by these difficulties. Limited to the baselines he can measure on the earth, the astronomer must set one observer in one hemisphere, another in the other. Each observer must have his own set of instruments, and every observation which one has made in summer will have to be compared with an observation which the other has made in winter. Thus we can understand the astronomers should have failed totally when they attempted to determine the sun's distance without aid from other celestial bodies. It may seem at first sight as though nothing the other celestial bodies could tell the astronomer would be of the least use to him, since these bodies are for the most part farther off than the sun, and even those which approach nearest to us are still far beyond the limits of distance within which the simple plan followed by surveyors would be of any service. And besides, it must be supposed that information about the distance of one celestial body could be of no particular service towards the determination of the distance of another. But 2 things aid the astronomer at this point. First of all, he has discovered the law which associates together the distances of all the planets from the sun, so that if he can determine the distance of any one planet, he learns immediately the distance of all. Secondly, the planets in their motion travel occasionally into such position that they become mighty indices, tracing out a natural dial plate, the significant lesson from which the astronomer hopes to learn so much. To take an instance from the motions of another planet than the one we are dealing with. Mars comes sometimes so near the Earth that the distance separating us from him is little more than 1/3 of that which separates us from the sun. Suppose that, at such a time, he is seen quite close to a fixed star. That star gives the astronomer powerful aid in determining the planet's distance. For, to observers in some parts of the Earth, the planet will seem nearer to the star than he will to observers elsewhere. A careful comparison of the effects thus exhibited will give significant evidence respecting the distance of Mars, and we see that the star has served as a fixed mark upon the vast natural dial of the heavens, just as the division marks on a clock face serve to indicate the position of the hands. Now we can at once see why Venus holds so important a position in this sort of inquiry. Venus is our nearest neighbor among the planets. She comes several millions of miles nearer to us than Mars, our next neighbor on the other side. That this is the primary reason of her being so much considered by astronomers. But there is another of equal importance. Venus travels nearer than our Earth to the Sun, and thus there are occasions when she gets directly between the Earth and the Sun. At these times she is seen upon his face, and his face serves as a dial plate by which to measure her movements. When an observer at one part of the Earth sees her on one part of the Sun's face, another observer at some other part of the Earth will see her on another, and the difference of the position, if accurately measured, would at once indicate the Sun's distance. As a matter of fact, other modes of reading off the indications of the great dial plate have to be adopted. Before proceeding to consider these modes, however, we must deal with one or two facts about Venus's movements, which largely affect the question at issue. Let us first see what we can gain by considering the distance of Venus rather than that of the Sun. At the time of a transit, Venus is, of course, on a line between the Earth and the Sun, and she is somewhat less than a third of the Sun's distance from us. Thus, whatever effect on observers' change of place would produce upon the Sun would be more than trebled in the case of Venus. But it must not be forgotten that we are to judge the motions of Venus by means of the dial plate formed by the solar disk, and that dial plate is itself shifted as the observer shifts his place. Venus is shifted 3 times as much, it is true, but it is only the balance of change that our astronomers can recognize. That balance is, of course, rather more than twice as great as the Sun's change of place. So far, then, we have not gained much, since it has been already mentioned that the Sun's change of place is not measurable by any process of observation astronomers can apply. It is to the fact that we have the Sun's disk, whereby to measure the change, that we chiefly trust, and even that would be insufficient were it not for the fact that Venus is not at rest, but travels athwart the great solar dial plate. We are thus enabled to make a time measurement take the place of a measurement of space. If an observer in one place sees Venus across the Sun's face at a certain distance from the center, while an observer at another place sees her follow a path slightly further from the center, the transit clearly seems longer to the former observer than to the latter. This artifice of exchanging a measurement of time for one of space, or vice versa, is a very common one among astronomers. It was Edmund Halley, the friend and pupil of Sir Isaac Newton, who suggested its application in the way above described. It will be noticed that what is required for the successful application of the method is that one set of observers should be as far to the north as possible, another as far to the south, so that the path of Venus may be shifted as much as possible. Clearly, the northern observers will see her path shift as much to the south as it can possibly be, while the southern observers will see the path shift as far as possible towards the north. One thing, however, is to be remembered. A transit lasts several hours, and our observers must be so placed that the sun will not set during these hours. This consideration sometimes involves a difficulty, for our Earth does not supply observing room all over her surface, and the region where observations would be most serviceable may be covered by a wide, extended ocean. Then again, the observing parties are being rapidly swayed around by the rotating Earth. It is often difficult to fix on a spot, which may not, through this case, be shifted from a favorable position at the beginning of the transit to an unfavorable one at the end. Without entering all the points of difficulty involved by such consideration as these, I may simply indicate the fact that the astronomer has a problem of considerable complexity to solve in applying Halley's method of observation to a transit of Venus. It was long since pointed out by the French astronomer Delia that the subject may be attacked another way, that in fact, instead of noticing how much longer the transit lasts in some places than in others, the astronomer may inquire how much earlier it begins or ends in some places than in others. Here is another artifice, extremely simple in principle, though not altogether so simple in its application. My readers must bear with me while I briefly describe the qualities of the second method, because in reality the whole question of the transit and all the points which have to be attended to in the equipment and placing of the various observing parties depend on these preliminary matters. Without attending to them, or at least to such primary points as I shall select, it will be impossible to form a clear conception of the circumstances with which astronomers have to deal. There is, however, no real difficulty about this part of the subject, and I shall only ask of the reader to give his attention to it for a very brief space of time. Suppose the whole of that hemisphere of the earth on which the sun is shining when the transit is about to begin were covered with observers waiting for the event. As Venus sweeps rapidly onwards to the critical part of her path, it is clear that some of these observers will get an earlier view of the commencement of the transit than others will, such as at a boat race, persons variously placed round a projecting corner of the course see the leading boat come into a view at different times. Some one observer on the outer rim of the hemisphere would be absolutely the first to see the transit begin. Then, rapidly, other observers would see the phenomenon, and in the course of a few minutes, some one observer on the outer rim of the hemisphere, most exactly opposite the first, would be absolutely the last to see the transit begin. From that time, the transit would be seen by all for several hours. I neglect the Earth's rotation for the moment. But the end of the transit, like the beginning, would not be seen simultaneously by the observers. First one would see it, then in succession the rest, and last of all an observer almost exactly opposite the first. Now here we have to consider 4 observers who occupy exceptional positions. There is 1, the observer who sees the transit begin earliest; 2, the one who sees it begin latest; 3, the one who sees it end earliest; and 4, the one who sees it end latest. Let us consider the first 2 only. Suppose these 2 observers afterwards compare notes, and found out what was the exact difference of time between their respective observations. It is not clear that the results would at once afford the means of determining the sun's distance. It would be the simplest of all possible astronomical problems to determine over what proportion of her orbit Venus passed in the interval of time which elapsed between these observations. And the observers would now have learned that that portion of Venus's orbit is so many miles long, for they know what distance separated them, and it would be easy to calculate how much less that portion of Venus's orbit is. Thus they would learn what the length of her whole orbit is, thence her distance from the sun, and thence the sun's distance from us. The 2 observers who saw the transit end earliest and latest could do the like. Generally speaking, and neglecting all the complexities which delight the soul of the astronomer, this is Delia's method of utilizing a transit. It has obviously one serious disadvantage as compared with the other. An observer at one side of the Earth has to bring his observations into comparison with those made by an observer at the other side of the Earth. Each uses the local time of the place at which he observes, and it has been calculated that for the result to be of value there must not be an error of a single second in their estimates of local time. Now, does the reader appreciate the full force of this proviso? Each observer must know so certainly in what exact longitude he is, that his estimate of the time when true noon occurs shall not be 1 second wrong. This is all satisfactory enough in places where there are regular observatories, but matters are changed when we are dealing with such places as Wahoo, Kerguelen Land, Chatham Island, and the wilds of Siberia. In the transit of 1874, there are so many such difficulties to be encountered. In fact, it is almost impossible to conceive a transit, the circumstances of which are more inconvenient. On the other hand, however, the transit is of such a nature that if once the preliminary difficulties are overcome, we can hope more from its indications than from those of any other transit, which will happen in the course of the next few centuries. The transit will begin earliest for observers in the neighborhood of the Sandwich Islands, latest for observers near Crozet Island, far to the southeast of the Cape of Good Hope. It ends earliest for observers far to the southwest of Cape Horn, latest for observers in the northeastern part of European Russia. Thus we see that, so far as the application of our second method is concerned, the suitable spots are not situated in the most inviting regions of the Earth's surface. As the transit happens on December 8, 1874, the principal northern stations will be very bleak abodes for the observers. The southern stations are in yet more dreary regions, notwithstanding the fact that the transit occurs during the summer of the southern hemisphere. For the application of Halley's method, we require stations where the whole transit will be visible, and as the days are very short at the northern stations in December, it is as respects these that we encounter most difficulty. However, it has been found that many places in northern China, Japan, eastern Siberia, and Manchuria are suited for the purpose. The best southern stations for this method lie, unfortunately, on the unexplored Antarctic continent and the islands adjacent to it. But Crozet Island, Kerguelen Land, and some other places more easy of access than the Antarctic continent will serve very well. Indeed, England has so many stations to occupy elsewhere that it is doubtful whether she will care to undertake the dangerous and difficult task of exploring the Antarctic waste to secure the best southern stations. The work may fairly be left to other nations, and doubtless will be efficiently carried out. What England will actually undertake has not yet been fully decided upon. We may be quite certain that she will send out a party to Oahu or Hawaii to observe the accelerated commencement of the transit. She will also send observers to watch the retarded commencement, but whether to Crozet Island, Kerguelen Land, Mauritius, or Rodriguez is uncertain. Possibly 2 parties will be sent out for this purpose, and most likely to Rodriguez and Mauritius will be the places selected. It had been thought until lately that the sun would be too low at some of the places when the transit begins, but a more exact calculation of the circumstances of the transit has shown this to be a mistake. Both Crozet Island and Kerguelen Land are very likely to be enveloped in heavy mists when the transit begins, and that is soon after sunrise. Hence the choice of Mauritius and Rodriguez as the most suitable station. England will also be called on to take an important part in observing the accelerated end of the transit. A party will probably be sent to Chatham Island or Campbell Island, not far from New Zealand. It has been thought that at the former island the sun would be too low, but here, again, a more exact consideration of the circumstances of the transit has led astronomers to the conclusion that the sun will be quite high enough at this station. The Russian observers are principally concerned with the observation of the retarded end of the transit, nearly all the best stations lying in Siberia. But there are several stations in British India where this phase can be very carefully observed. And doubtless the skillful astronomers and mathematicians who are taking part in the survey of India will be invited, as at the time of the great eclipse, to give their services in the cause of science. Alexandria also, though inferior to several of the Indian stations, will probably be visited by an observing party from England. It will be seen that England will thus be called on to supply about 6 expeditions to view the transit. All these will be sent out in pursuance of Delille's mode of utilizing a transit. So that, for reasons already referred to, it will be necessary that we should be provided with instruments of the utmost delicacy and very carefully constructed. They will have to remain at their several stations for a long time before the transit takes place, several months at least, so that they may accurately determine the latitude of the temporary observatories they will erect. This is a work requiring skilled observers and recondite processes of calculation. Hence it is that the cost of sending out these observing parties is so considerable. The only English party which will apply Halley's method of observation is the one which will be stationed at Mauritius under Lord Lindsay. This part of their work will be comparatively easy, the method only requiring that the duration of the transit should be carefully timed. In fact, one of the great advantages of Halley's method is the smallness of the expense it involves. A party might land the day before the transit and sail away the day after. with results at least as trustworthy as those which a party applying Delia's method could obtain after several months of hard work. It is to this, rather than any other cause, that the small expense of the observation made in 1769 is to be referred. And doubtless had it been decided by our astronomical authorities to apply Halley's method solely or principally, the extent of the transit observations would have been materially lessened. There would, however, have been a risk of failure through the occurrence of bad weather at the critical stations, whereas now, as other nations will doubtless avail themselves of Halley's method, the chance that the transit observations will fail through meteorological causes is very largely diminished. Science will owe much to the generosity of England in this respect. It is indeed only recently that the possibility of applying Halley's method has been recognized. It had been thought that the method must fail totally in 1874. But on a more careful examination of the circumstances of a transit, a French astronomer, M. Puiseux, was enabled to announce that this is not the case. Almost simultaneously, I published calculations pointing to a similar result. But having carried the processes a few steps further than M. Puiseux, I was able to show that Halley's method is not only available in 1874, but is the more powerful method of the two. Unfortunately, there is an element of doubt in the inquiry, of which no amount of care on the part of our observers and mathematicians will enable them to get rid of. I refer to the behavior of Venus itself. It is to the peculiarity we are now to consider that the quasi-failure of the observations made in 1769 may be attributed. It is true that Mr. Stone, the first assistant of the Greenwich Observatory, has managed to remove the greatest part of the doubt which clouded the results of those observations. But not even his skill and patience can serve to remove the blot which a century of doubt has seemed to throw upon the most exact of sciences. We shall now show how much of the blame of that unfortunate century of doubt is to be ascribed to Venus. At a transit, astronomers confine their attention to one particular phase, the moment, namely, when Venus just seems to lie wholly within the outline of the sun's disk. This, at least, was what Halley and Delia both suggested as desirable. Unfortunately, Venus had not been consulted, and when the time of the transit came, she declined to enter upon or leave the sun's face in the manner suggested by the astronomers. Consider, for example, her conduct when entering on the sun's face. At first, as the black disk of the planet gradually notched the edge of the sun's disk, all seemed going on well. But when somewhat more than half of the planet was on the sun's face, it began to be noticed that Venus was losing her rotundity of figure. She became gradually more and more pear-shaped, until at last she looked very much like a peg top touching with its point the edge of the sun's disk. Then suddenly, as by a lightning flash, said one observer, the top lost its peg, and then gradually Venus recovered her figure, and the transit proceeded without further change on her part until the time came for her to leave the sun's face, when similar peculiarities took place in a reversed order. Here was a serious difficulty indeed, for when was the moment of true contact? Was it when the peg-top figure seemed to just touch the edge of the sun? This seemed unlikely, because a moment after the planet was seen well removed from the sun's edge. Was it when the rotund part of the planet belonged to a figure which would have touched the sun's edge if the rotundity had been perfect elsewhere? This again seemed unlikely, because at this moment the black band connecting Venus and the sun was quite wide. And besides, if this were the true moment of contact, what eye could be trusted to determine the occurrence of a relation so peculiar? Yet the interval between this phase and the final, or peg-top phase, lasted several seconds, as many as 22 in one instance in 1769. And the whole success of the observation depended on exactness within 3 or 4 seconds at the outset. We know that Venus will act in precisely the same manner in 1874. If we had been induced to hope that improvements in our telescope would diminish the peculiarity, the observations of the transit of Mercury in November 1868 would have sufficed to destroy that hope. For even with the all but perfect instruments of the Greenwich Observatory, Mercury assumed the peg-top disguise in the most unpleasing manner. It may be asked, then, what do astronomers propose to do in 1874 to prevent Venus from misleading them again as she did in 1769? Much has already been done towards this end. Mr. Stone undertook a series of careful researches to determine the law according to which Venus may be expected to behave or to misbehave herself, and the result is that he has been able to tell the observers exactly what they will have to look for, and exactly what it is most important that they should record. In 1769, observers recorded their observations in such doubtful terms, owing to their ignorance of the real significance of the peculiarities they witnessed, that the mathematicians who had to make use of those observations were misled. Hinc ille lacrimae. Hence it has that an unobserved reproach was fallen upon the exact science. The amount of the error resulting from the misinterpretation of the observations made in 1769 was, however, very small indeed, when its true character is considered. It is indeed easy to make the error seem enormous. The sun's distance came out some 4 million of miles too large, and that seems no trifling error. Then again, the resulting estimate of the distance of Neptune came out more than 100 million miles too great, while even this enormous error was as nothing when compared with that which resulted when the distance of fixed stars were considered. But this is an altogether erroneous mode of estimating the effect of the error. It would be as absurd to count up the number of hair's breadth by which the geographer's estimate of the length and breadth of England may be in error. In all such matters it is relative and not absolute error we have to consider. A microscopist would have made a bad mistake who should overestimate the length of a fly's proboscis by a single hair's breadth. But the astronomer had made a wonderfully successful measurement of the sun's distance, who deduced it within 3 or 4 millions of miles of the true value. For it is readily calculable that the error in the estimated relative bearing of the sun, as seen from opposite sides of the earth, corresponds to the angle which a hair's breadth subtends when seen from a distance of 125 feet. The error was first detected when other modes of determining the sun's distance were applied by the skillful astronomers and physicists of our own day. We have no space to describe as fully as they deserve the ingenious processes by which the great problem has been attacked without aid from Venus. Indeed, we can but barely mention the principles on which those methods depend. But to the reader who takes an interest in astronomy, we can recommend no subject as better worth studying than the masterly researches of Foucault, Leverrier, and Henson upon the problem of the sun's distance. The problem has been attacked in 4 several ways. First, the tremendous velocity of light has been measured by an ingenious arrangement of revolving mirrors. The result, combined with the known time occupied by light in traveling across the sun's orbit, immediately gives the sun's distance. Secondly, a certain irregularity in the moon's motion, due to the fact that she is most disturbed by the sun when traversing the half of her path which is nearest to him, was pressed into the surface with similar results. Thirdly, an irregularity in the Earth's motion, due to the fact that she circles around the common center of gravity of her own mass and the moon's, was made a means of attacking the problem. Lastly, Mars, a planet which, as we have already mentioned, approaches us almost as nearly as Venus, was found an efficient ally. The result of calculations found on these methods shows that the sun's distance, instead of being about 95 million miles, is a little more than 91,500,000 miles. And recently, a re-examination of the observations made upon Venus in 1769 led Mr. Stone to believe that they point to a similar result. Doubtless, however, we must wait for the transit of Venus in 1874 before forming a final decision as to the estimate of the sun's distance which is to take its place in popular works on astronomy during the next century or so. Nothing but an unlooked-for combination of unfavorable circumstances can cause the failures of our hope. Certainly, if we should fail in obtaining satisfactory results in 1874, the world will not say that the generosity of the English government has been in fault, since it would be difficult to find a parallel in the history of modern science to the munificence of the grant which has been made this year for expenditures to observe a phenomenon whose interest and importance are purely scientific. End of section 6.